exactly what that's about. So go ahead, share your screen, and people feel free to interrupt David at any time or send messages in the chat. Wait to the end where there'll be more questions. David.
Yes, absolutely. Great. Let me just, you can see my screen now. Let me just move your window so I can see all of you and the slides. Great, thank you. Thanks, Ephraim, for the introduction. As Ephraim mentioned, I work in his lab on a Bose-Einstein condensate apparatus. And the work I'm going to tell you about today is sort of peripherally connected to the main work of my PhD, but concerns a technique that is Deltakick cooling that we've used in the lab throughout my PhD, rather successfully, unlike Charlie Brown right here, to reduce the momentum spread of our BEC in a way that preserves the phase space density. But despite the fact that Deltakick cooling in its standard construction doesn't include the interactions between our atoms, it's been remarkably successful. But one thing we would like to do, one thing that motivated this work, was being able to describe Deltakick cooling in the case of an interacting quantum gas. And in particular, oops, trying to show you my laser pointer here. Now maybe you see a laser pointer. In particular, the way we've been able to describe Deltakick cooling for interacting quantum gases is by leveraging a variety of systems that exhibit scale-invariant dynamics. And I'll tell you what that means a little bit later in the talk. So the full title of the manuscript that came out of this work is a bit more long-winded. I think this is the first manuscript I've been a part of that has an Oxford comma in the title. The full title is Exact Deltakick Cooling, Time Optimal Control of Scale-Invariant Dynamics, and Shortcuts to Adiabaticity Assisted by Kicks. And the reason for this long-winded title is because in addition to understanding Deltakick cooling for interacting gases, we also wanted to understand how Deltakick cooling related to other protocols for cooling, which have been well studied. So Deltakick cooling is a technique for cooling, as I said, that preserves phase space density. So its output, its byproduct, is equivalent to adiabatic expansion. Here you're seeing a wave packet in a time-dependent harmonic oscillator. And by the adiabatic theorem, if our time-dependent Hamiltonian is varying slowly enough so that we always remain in the instantaneous eigenstate of this oscillator, then we can adiabatically expand from a tightly confined wave packet to a broad one, and thereby reduce the momentum spread at the cost of increasing spatial density. Deltakick cooling does the same thing, but in a much faster time compared to adiabatic expansion. And so as a result, it's in this category of techniques known as shortcuts to adiabaticity. Here I'm showing you a variety of different protocols that implement a shortcut to adiabaticity. With respect to the dotted black line here is an adiabatic expansion. And all of them produce the same output final state. So another motivation for this work was understanding how Deltakick cooling relates to other shortcuts to adiabaticity. If you're interested in a review article, I would suggest this one here. And in the field of shortcuts to adiabaticity, a big question is, what are the optimal protocols? What are the speed limits that limit how quickly I can transition my system from one eigenstate of an initial Hamiltonian to a different eigenstate of a final Hamiltonian? So another connection that our work makes is understanding Deltakick cooling compared to other time optimal protocols, and including, for us, in this case, the interactions. We're understanding this within the context of scale-invariant dynamics.
Can I ask a question?
Yes.
So here in the y-axis, are the omega's frequencies?
So here, this these adiabatic protocols are modifying the trap frequency of a harmonic oscillator.
Okay, so what does it mean to have a negative frequency squared here?
So it means having an imaginary frequency, which corresponds to a repulsive potential. Minus omega squared is an inverted oscillator. We'll come back to that later in the talk.
Okay, thanks.
Yep.
David, can I ask another question, please?
Yeah, Ilya.
Hi. So is there a condition? So usually in shortcut to adiabaticity, there's a condition where you want your essentially final state to be the same, even with the same phase with the, say, the adiabatic time evolution, right?
Mm-hmm.
So in that case, there are conditions such as the first derivative and the second derivative should vanish. And if you have delta functions, that does not happen. So how do you reconcile this?
So the derivatives you need to cancel are derivatives in the expansion of the wave packet in the case of a harmonic oscillator. I don't think you need the derivatives to vanish in the case of the actual parameters that you are varying in the Hamiltonian. But or maybe what you're referring to is, so the adiabatic condition is in the harmonic oscillator case includes omega dot. Maybe that's what you're asking. And some of these protocols here have sharp jumps. So these sharp jumps don't correspond to adiabatic protocols. They correspond to shortcuts to adiabaticity that results in the same final state, but the protocol itself isn't an adiabatic one. Was that your?
No, but maybe we could discuss it later. Thanks.
Okay. Okay, so my hope is that this talk will touch on all aspects of this title and many aspects of the manuscript itself. In order to sort of connect these different fields, a collaboration was appropriate. And in particular, we collaborated with Léonce Dupéy and Adolfo Del Campo at the University of Luxembourg, who are really sort of the experts in these shortcuts to adiabaticity and time optimal control. And at the University of Toronto, me and Ephraim Steinberg have worked on this project. Okay, so today's story is going to try to touch on all those topics. But first, I'll review the standard construction of ideal Deltakick cooling, which was originally viewed from a classical perspective. We'll then review what scale-invariant dynamics are and some systems that obey scale-invariant dynamics. And within that description of interacting quantum systems, we'll come up with an exact conception of Deltakick cooling, which will allow us to consider a broader class of protocols, ones in fact that include repulsive potentials. And we will analyze what are the speed advantages of these new modified Deltakick protocols. So that's the plan for today. We'll start with the ideal conception of Deltakick cooling, which, as I said, we'll look at from a classical perspective. In the classical approximations, the initial trap, I've actually drawn sort of to emphasize an inharmonicity here, doesn't need to be a harmonic trap, though in our treatment, in our exact treatment, we will assume an initial harmonic confinement. But in the classical construction, all that's required is that the initial cloud of particles are tightly confined to some region Z0. And I should mention that this was originally conceived in 1986 by Chiu et al., but it was extended to a quantum description where these particles are now wave packets in 1997, but still non-interacting. All right, so if we start with this cloud of particles tightly confined at t equals 0, and we allow them to expand for a time tf, long compared to the ratio of the initial confinement to the average initial thermal velocity. Then if we track the ith particle here, then its position, Zi, is approximately linear in the expansion time and the initial velocity. And I say approximately because what we're by doing this long time of flight, what we're ignoring is the dependence of the final velocity on the the dependence of the final position on the initial position. If after that time of expansion, we apply a harmonic potential, then the impulse received, the momentum kick received by this ith atom is also linear in its final position and also in the duration of the kick. And so if we set this kick such that it's equal to the final momentum of the particle, well, the final velocity was again linear in its position. And so not only will this kick cancel this momentum, bring the atom or the particle to rest after this kick, but in fact, this final position, Z, on both sides of the equation drops out of the problem. And so in fact, we bring all particles at any final position Z to rest if this condition holds. In other words, we've matched the strength of our kick, that's what we refer to as omega squared tau, to 1 over the expansion time. And if we do that, then the harmonic oscillator, for a perfect harmonic oscillator, we've brought all of our atoms to rest. Temperature is 0, ideally. In reality, of course, a variety of factors place practical limits on the cooling performance of Deltakick cooling. And we can see them pretty easily by understanding that protocol in an analogy with lenses. So in the description I just gave, we started with a point source. We were ignoring the initial extent of our source of atoms. We allowed these rays to expand. And then we applied a short lens which collimated all of these rays. And so in this analogy, the focal, instead of the focal length, we have a focal time. And if we match that focal time equal to 1 over the kick strength, then we've collimated our rays of light. Of course, the first thing you would think of to set a practical limit on this is, what if we don't have a point source? We have a source with a finite extent. Then you'll see that rays that don't come from the center of this object are not perfectly collimated. And so the extent to which we can't ignore the initial size of our cloud of atoms or the size of our source here places limits on the cooling performance. Also, from this analogy, you might come up with other practical limits. For instance, if our lens has aberrations in it, in the case of or that might manifest itself in anharmonic components of our trapping potential. And you might imagine that if this lens isn't thin and we had aberrations, then our kick wouldn't obey this equation. We can also look, an intuitive way to understand Deltakick cooling is also in phase space, where we can look at these classical phase space trajectories. We start with our atoms in a harmonic trap, and when we release them at t equals 0, they expand. So positive momentum shift to the right here, negative momentum shift to the left, and after a long expansion time, position and momentum become strongly correlated. And when we apply our Deltakick, this distribution begins to rotate at the oscillator frequency of our kick. And if we stop that rotation at the point where our distribution aligns with the x-axis, then we've minimized the extent in the vertical direction. We've minimized the momentum spread. Of course, if we waited a quarter period more, we would have done the opposite. We would have minimized the spatial extent and maximized the momentum spread. But if we wait only so that we align the distribution with this x-axis, we've minimized the final momentum spread. Looking in phase space, we also quickly realized that since all of our forces are conservative, Liouville's theorem guarantees that phase space area is conserved. So the factor by which we can compress the momentum distribution is related to the factor by which our cloud is expanded. A quantum mechanical treatment basically yields the same results. And in particular, the Wigner distribution in a harmonic oscillator and in free space is identical to that of the classical case. And so if I wanted to look at the Wigner distribution here, all I have to do is really shade in these phase space trajectories. And again, we have the important observation that the distribution of our final momentum is related to the expansion factor of our cloud. We're trading off momentum, variance in momentum for a larger variance in position. So as I said before, Deltakick cooling falls into the category of cooling protocols that preserve phase space density. Just at the turn of the century, these protocols came into experimental demonstrations. And here I'll show you a few of them. And I've relabeled some of the axes so they're more readable for us. They're not quite in the units of the original papers. But the first demonstration, I believe, was in a cesium lattice in Paris. And what they looked at is the momentum reduction factor. So here you can see they've, at their best down here, they've reduced by about a factor of 4 as a function of the time of their kick held in a lattice. So ideally, this dashed line shows what you'd expect in a pure harmonic oscillator, that at one time you have aligns the distribution with the x-axis, and so you minimize the momentum spread, and at another time you've maximized it. And what they saw is that there was some anharmonicity in their track due to different oscillation frequencies at different vertical positions in their track. So for longer pulse sequences, those different oscillation frequencies resulted in worse cooling. In the same year, another French group, showed Deltakick cooling in a slightly different scenario. Here they created their trapping potential with a magnetic field. So the x-axis, though I'm saying it's kick strength, it's really amps in a coil somewhere. And here they're looking explicitly at the cloud size at 2 different times given by the squares and the triangles. The squares were at the first time, and the triangles are at the second time. So this point where I've drawn this arrow, where at the 2 times the cloud has not expanded after the kick very significantly, corresponds to when I have done my best collimation of the cloud. I've reduced the momentum spread as best I can. What's interesting here is the minimum in the triangular data corresponds not to collimating the cloud, but instead putting my lens not a focal time away, but a different time, and creating an image of the object. So this is in the thin lens equation, looking for a given object distance and a given focal length at one image distance away when the cloud refocuses. And then published in the next year, Ephraim's group, before I was here many years ago, also showed Deltakick cooling, where here you're explicitly looking at the cloud size expansion as a function of time for different kick strengths. And in particular, you can see this one line here, which barely expands as a function of time, corresponds to the best cooling performance. And the numbers here are pretty impressive. If we take these variances in final momentum and calculate an effective temperature, given by this equation here, we get numbers that are hundreds of nanokelvin. More recently, the cooling performance has improved, not only because Deltakick cooling has improved, but also because other cooling techniques have improved. In my time at University of Toronto, we've actually done Deltakick cooling down to 900 picokelvin in a Bose-Einstein condensate of rubidium-87. Here you're looking at, again, the expansion after the kick of the cloud as a function of time. In the red, comparing the unkicked cloud, and in the blue, the kicked cloud, and you can see that it barely expands at all. So actually, in order to measure this temperature, we had to innovate a new technique to measure the temperatures of such low clouds. And if you're interested, you can take a look at the paper here. Another group has done remarkably well. The Kasevich group has cooled down. I think this might still be the record for cooling, getting down to 500 picokelvin, which they were able to do by doing extraordinarily long time of flights. By launching their cloud up a 10-meter tube, they can do extremely long time in flight, and as a result, reach low temperatures because their final cloud size before the kick is many factors larger than the initial cloud size. So all of this is to say that Deltakick cooling has been remarkably successful, despite the fact that our description of it doesn't include the interactions between these particles. So that's what we'd next like to be able to do. And an elegant approach to many interacting quantum systems is using scale invariance, otherwise known as self-similar evolution. And what a scaling solution does is it maps the non-equilibrium equations of motion, so the expanding cloud, to an equilibrium many-body equation. So in other words, it shifts the difficult problem of solving for the time-dependent many-body wave function to solving a time-independent equation, where the Hamiltonian, or that equation of motion, has been scaled by particular scaling factors, which themselves contain the time dependence. So instead of having to solve a time-dependent many-body equation, we now only have to solve a time-independent Schrodinger equation, and then a time-dependent set of equations for the different scaling parameters. Maybe here I actually should have labeled this psi as a different psi. So this psi on the right-hand side is one which obeys a time-independent equation of motion. But in the cases that we'll be paying attention to here, at t equals 0, we'll assume that our full non-equilibrium many-body wave function corresponds to the equilibrium state. So we're starting in an equilibrium condition at t equals 0. So if we can solve a equilibrium scenario, a time-independent equation of motion, and then solve a time-dependent equation for particular scaling parameters, we have a solution for, or a scale-invariant solution. In particular here, our time-dependent equation for the scaling parameter of the position. So generally, there might be many scaling parameters. But in the case that we start in an equilibrium scenario, in the case that we start in an eigenstate of our Hamiltonian, and our interactions are time-independent, then the equation of motion for our scaling parameter takes the following form. This is known as an Irmakov equation, and it was first discovered in 1880 and has been very well studied. So if we can solve this equation of motion, oh, and I should also say that these omegas are our initial trap frequency and our final trap frequency. And it's only in the case that under the assumptions that I just mentioned, that we start in an equilibrium, and we start in an eigenstate of our Hamiltonian, and we have time-independent interactions, that these coefficients here are the real trap frequencies of our time-dependent Hamiltonian. Okay, so what systems obey scale-invariant evolution? Well, we've sort of implied that non-interacting wave packets in a harmonic oscillator do. So in that sense, non-interacting Bose and Fermi gases already obey scale-invariant evolution in a harmonic oscillator, but so do interacting ones. In particular, Bose-Einstein condensates and the Thomas Fermi regime do, as do one-dimensional gases in the Thomson-Gerardo regime, and so do 3D unitary Fermi gases. And the thing that all of these systems have in common that allows a scale invariant solution to hold is that their interaction potential obeys this scaling law here. And it's under that condition that all of these systems obey a particular symmetry that allows this scaling solution to hold. Okay, so now contained to the set of systems that obey scale invariant dynamics, which is a broad one, let's see if we can come up with an exact construction of Deltakick cooling. Well, a more generalized approach to Deltakick cooling would be to imagine, let's start in a harmonic potential of initial frequency omega naught. We do some expansion with an arbitrary time-dependent trap. And our goal is to end up in an eigenstate of a final trap with, which is also a harmonic oscillator with trap frequency omega f. Well, the first thing we can do is, because our system obeys the scaling condition, well, we can always match the width of our expanding cloud to a harmonic oscillator that has the same width eigenstate. So just by matching the size of our final trap to our expanding cloud, we've matched the size of the distributions. But that doesn't mean we have an eigenstate with respect to that final Hamiltonian, because in particular, we can have operator-dependent phase factors in front of this wave function right here. And it's not obvious, but under the assumptions I just outlined, the relevant operator-dependent phase factor is this one right here. We've gained a quadratic phase, or a phase quadratic in the position, because we started in a harmonic oscillator. And in a classical sort of interpretation of this expansion, this b dot over b looks like a local velocity of the expanding cloud. So it's this phase factor that is preventing the eigenstate, or that is preventing our system, which if we've matched the size of the cloud appropriately, that it's this phase factor that's preventing us from being an eigenstate of this final Hamiltonian. So if we can cancel that phase factor with a kick, then we're good to go. Here, this is the phase acquired from a Deltakick. Again, it's a harmonic kick, so we're applying a phase quadratic in position, and the kick strength again shows up here as this omega k squared times tau k, the duration of our kick. So if you stare at this long enough, you'll notice that most of these variables cancel, and we can cancel this excitation, or this phase factor, by setting the strength of our kick equal to this combination of the scaling factor b dot being the time derivative at the time of the kick over the scaling factor b at the time of the kick. And this is the main result of this work, that we can now calculate the strength of the kick required to cancel excitations of the expanding cloud, given that we can solve for the time dependence of the scaling factor. So we can now do this for a given expansion protocol. And in particular, maybe the first interesting thing to do would be to calculate the kick for a standard Deltakick cooling protocol. So we just are looking at free space expansion. Well, to do that, we need to solve the Irmakov equation with these initial conditions, that it's initially at equilibrium. The scaling factor is initially 1. And when we do that, we get this expression here, which we can compare to the ideal classical kick, where kick strength was just 1 over the expansion time. And what we see here is that in the long expansion time limit, these two things coincide, which is nice. That's, I guess, what we expected. Here I'm showing you sort of normalized expansion time, normalized to the initial harmonic oscillator frequency, and on the y-axis, log of the kick strength. So it's at early expansion times that these things disagree. Or we can look at this in terms of, we can look at the kick strength in terms of the cloud size. And what we see here is that when the scaling factor has increased by a factor of 4 or 5, that's when the exact expression for Deltakick cooling agrees with the ideal kick from the standard classical construction. All right. But now this is we can exploit this equation to maybe do something more interesting. This is a little bit more powerful than standard Deltakick cooling in that we can find this kick strength for an arbitrary expansion protocol. So in particular, we're interested in, is there some time-dependent trap frequency which will get us to our final state just before the kick faster than this free space expansion? That would be a faster protocol. Well, as Batuhan was bringing up at the beginning of this talk, one protocol to do that would be a repulsive potential. So that corresponds to setting our trap frequency in the expansion phase to imaginary number. And we can kind of intuitively see that, well, if we have a repulsive potential, then our cloud will expand faster. So let's see what we can get intuition just classically from that. Well, the phase space trajectories for an attractive harmonic oscillator are these elliptic ones here. They're periodic. But in an inverted oscillator, just because of this sign flip, now we have these hyperbolic, these phase space trajectories, which are hyperbolas in these two quadrants for the positive, these are the positive energy quadrants. And if you stare at the equations of motion, it's not difficult to see that there's a linear combination of momentum and position that expands exponentially with time. And it's maybe intuitive. If you put a particle here, it starts rolling down, accelerating very quickly away from the origin. What do the Wigner distributions look like? Well, in free space, we said, well, momentum is conserved. So this positive momentum here shifts to the right, the negative momentum here shifts to the left. But with expansion in an inverted oscillator, for the same time of expansion, the cloud sort of shears much more quickly, and we increase the momentum of the cloud. But let's use our exact expression and understand how this behaves. Well, we need, again, to solve the Armakov equation with these initial conditions. And what we see is our kick strength is approximately equal to the trap frequency of the inverted oscillator. And that's because, as I was alluding to a moment ago, the scaling factor goes approximately exponentially with time. So this B dot brings down a factor of omega I, and the rest cancels. All right, let's compare the time advantage for these different protocols. And in particular, the parameter we were interested in looking at is how do these different protocols scale with the cooling factor? So with the ratio of the initial temperature of the cloud to the final temperature, which just from the definition of the effective temperature looks like the initial velocity squared over the final velocity squared. And again, because of Louisville's theorem, and because we're preserving phase space area, that's equivalent to the ratio of the final size of the clouds, the initial size squared, or the ratio of the trap frequencies. So what do we anticipate in the adiabatic case? Well, in the adiabatic case, we want our time-dependent Hamiltonian to always be slow with respect to the dynamics of the system, which in a harmonic oscillator is given by 1 over the trap frequency. So in a worst-case scenario, we want the time of this adiabatic protocol to be slow with respect to 1 over the final trap frequency. So if we rearrange this equation, that means that the time for our adiabatic protocols can go linearly with the cooling factor. What about Deltakick cooling? Well, in the long time expansion limit, we saw that the final cloud size goes linearly with the initial velocity. So plugging that in here for our final cloud size, we see that Deltakick cooling goes like the square root of the cooling factor. And then finally, for this new Deltakick cooling protocol where we do expansion in an inverted oscillator, we just saw that the final size goes approximately exponentially with time. So we maybe expect that the cooling protocol goes like, or the time for the protocol scales like the log of the cooling factor. And it turns out all of these expectations are approximately right. The expansion in the inverted oscillator goes like log of the cooling factor, Deltakick cooling goes like the square root of the cooling factor. And this coefficient here for the square root is approximately linear from the cooling factor. How does all of this compare to time optimal protocols? Well, it turns out that a set of time optimal protocols has already been conceived, and they're referred to as bang-bang protocols, and they set the standard. So for real trap frequencies in a harmonic oscillator, Solomon and others in 2009 showed that if your trap frequencies are limited, are bounded to some minimum and some maximum value, and you're trying to come up with a protocol to go from some initial trap omega I to some final trap omega F, then the time optimal protocol takes what's known as a bang-bang form, meaning you take sudden jumps between different values of the trap frequency, here omega 1 and omega 2. And in particular, the time optimal bang-bang protocol is when you saturate the bounds that your trap frequency is limited to. So the time optimal bang-bang protocol is when we jump between the minimum and the maximum values that we're allowed to have. And a year later, Stephanatos and others showed that when you include imaginary trap frequencies, in other words, when you include the possibility of having an inverted oscillator, the time optimal bang-bang protocols also, or the time optimal protocols also follow this bang-bang form. Now, in our work, we show this a bit more rigorously. We actually calculate these times, but you might have some intuition that if I allow, for instance, in the real trap frequency case, the minimum trap frequency to go to 0 and the maximum trap frequency to go to infinity, well, in that case, I can do a Deltakick, an instantaneous Deltakick. And so it's in that sense that Deltakick cooling, turns out with and without trap frequency, is equivalent to the time optimal bang-bang protocol that is unbounded in trap frequencies. So it's in that sense, when we have unbounded trap frequencies, in other words, instantaneous kicks, that Deltakick cooling is equivalent to the time optimal protocol. To give you maybe just one example, to give you an intuition of why that's the case, I'll show you a protocol that is in essence a bang-bang one. Imagine we initially start with a cloud confined in a harmonic trap with trap frequency omega naught, and it's released into a weaker trap. It's jumped down into a weaker trap with trap frequency omega 1. Well, as some of you might have some intuition for, the dynamics follow breathing oscillations. The cloud expands and contracts, expands and contracts. And the maximum size of the cloud is given by this ratio of omega naught over omega 1. And when the cloud reaches that maximum size at the 3/4 period, right before we start to compress, the scaling factor derivative is 0. In other words, all the velocities at all positions in a harmonic oscillator come to rest at the same time. So in this bang-bang protocol, the optimum time would be to, where here n equals 1, we've waited 1/4 period, and then we jump to a final trap, which matches the size of the cloud. We match the trap frequency of our final oscillator to the size of the cloud at that moment. And if we do that, we've done a bang bang protocol in a time pi over 2 omega 1. And if we write that in terms of the cooling factor, that looks like the square root of n, where n is the cooling factor. So just like in Deltakick cooling, which I showed you a moment ago, which scales like the square root of the cooling factor, here again, the bang bang protocol scales like the square root of the cooling factor. All right, so before I end, I will briefly summarize what I've shown you. The main result is that for scale invariant evolution, there's an exact approach to Deltakick cooling given by this equation, which allows us to calculate our kick strength for arbitrary scale invariant evolution, which is governed by the time dependence of the scaling factor. This describes Deltakick cooling in a broader class of cases. It describes it in interacting systems in arbitrary time-dependent harmonic traps that can either be repulsive or confining. And we've shown that when we include repulsive potentials, the Deltakick cooling protocol outperforms the conventional one. Finally, we've seen that this exact Deltakick cooling is equivalent to the time-optimal bang-bang protocols. And this opens the door for studying a broader class of shortcuts to adiabaticity assisted by kicks. The reason for that is standard shortcuts to adiabaticity tune the time dependence of the scaling factor to match an initial eigenstate with a final eigenstate of the final Hamiltonian. Here we have an additional degree of freedom, not just the time dependence of the harmonic oscillator during the expansion, but we also have a kick at the end. And so we can use the kick to cancel the phase factor in that equation I showed you, and use the protocol or the expansion of the time dependence of the harmonic oscillator to match the size. So with kicks, we sort of have an additional degree of freedom compared to standard shortcuts to adiabaticity. And finally, I'll just say that we have some hope that not only can we improve the speed of Deltakick cooling with repulsive potentials, but we also have some hope that we can actually improve the cooling performance as well by canceling aberrations. Similarly to how one might, in the analogy with lenses, cancel aberrations by using more than one lens. Here I'm showing you an achromatic lens, which is a composite lens comprised of two different lenses, where the index of refraction for the two lenses balances between these two wavelengths, the red and the blue. And so despite that they are picking up different phases in each lens, they focus to the same point. And we have some hope that we can do similar aberration canceling with multiple Deltakicks. So with that, I'll finish and welcome any questions.
Well, thank you very much, David. Applause, applause, applause. Even though I think you don't hear most of us, but everyone is. I see the hands showing up in the participant list. And let's open it up to questions. Someone? Anyone?
Not paying
This is
attention.
Joseph speaking.
Oh.
Hi, David.
Hi,
Thanks
Joseph.
for the great talk. I am reminded of this discussion about whether two-dimensional interacting systems are fully scale invariant or not. And this has kind of been a thread through the literature. I think started with a Pidievsky paper that more or less showed that classically they are. And then the follow-up was that there was a quantum correction missed, essentially that you can form a complete set of commuting observables so that even beyond the Gross-Ptowski equation, you have an exact scale-invariant system, except for the expectation value of the interactions, which is the contact. That shows you, that quantifies how broken the scale invariance is in a 2D system. I think that's understood well. And then, so that paper by Hoffman and others kind of sat around as this anomaly for, yeah, no pun intended, for a while. But then more recently, just last year, 3 different papers extended this and showed that the contact is more generally a good measure of the breaking of scale invariance in 3D systems as well. So, of course, you're doing something a little different because you have a dynamical system and then you're kicking it. And I don't know if that exactly carries over, but my suspicion is that you've used a Gross-Ptowski equation, and then you could wonder about the role of quantum depletion even at 0 temperature. But my guess is that if the contact is small, this works at all levels, and if the contact is large, this breaks down.
Yeah, so my understanding is that in the Thomas Fermi regime, regardless of dimension, BECs follow scale invariant dynamics. You're right. I also,
but that's a mean field picture, or is that including at all orders?
that's a mean field picture.
Yeah.
Now, I also have heard of sort of special case of 2 dimensions. And in some papers, yes, I had read that not in the Thomas Fermi regime. 2 dimensions is sort of a special case and follows scale invariance arbitrarily. And I'm not updated on the recent literature, but maybe you're saying that's an incorrect class that identically follows scale invariance. All of these, again, are for systems with contact interactions, in this case here. But yeah, in the terms that violate my understanding, the scale invariance for BC in 1 and 3 dimensions are because of the kinetic energy term. When you can't ignore the kinetic energy term at the edge of the cloud, the system doesn't identically follow scale invariance, and the correction terms are because of that.
But just to verify, David, you're still thinking in terms of beginning with the Gross-Ptowski equation, right? So you put in mean field from the beginning. And I think what Joseph is saying is there's a place where that breaks down.
Oh, yes, I'm assuming the Gross-Ptowski equation initially, mean field equation initially. That's right.
And am I right, Joseph, that what you're discussing is a beyond mean field breakdown of scale invariance?
Yeah, that's what I was wondering, because if you're asking about how interactions break this picture, I understand what you're saying, that for the BEC Thomas Fermi, you're neglecting kinetic energy.
Yeah, I guess my only point is, so I don't know about outside the mean field equation, but I guess my point is that already, even in the mean field description, a BC doesn't strictly follow scale invariance. It's only in the Thomas Fermi regime that BC follows scale invariance in 1, 2, and 3 dimensions. It's my understanding.
Mm-hmm.
I have a question, David.
And it sounds like Noah.
Yeah, Noah. From your presentation, it seems like there's a lot of similarities between what you're trying to do here and optical squeezing. In that here, it seems like you're trying to squeeze the momentum uncertainty into a broader position uncertainty. And in optical squeezing, you're trying to squeeze the uncertainty of one field quadrature into a bigger uncertainty in another field quadrature. Is there a mapping between these 2 tasks? And if there is there any like give and take between these 2 tasks, bodies of literature? any lessons to be learned?
I don't know what lessons there are to be learned. I do know that there is an analogy directly between, like how a beam can self-focus and preserve its spatial extent for over longer periods. I don't know if there are any great lessons to be learned there. I don't know that literature very well, but that analogy has been brought up in a variety of the Deltakick cooling papers I've read.
Well, I guess there's the self-focusing thing, which is the spatial wave function, but I'm more thinking about the electric field of the momentum quadrature and the position quadrature, and looking at people who are trying to do boson sampling type stuff where they need super high squeezing and they engineer crystals and cavities in specific ways to try and maximize the amount of squeezing they get in however many given finesse of their cavity. Are there any takeaways or communication between these two types of problems, or is it just physics are so different it's hard to compare?
So there could be. The short story is that I don't know. I will say that this operation, which brings this state to this state, does look like a squeezing transformation.
Mm-hmm.
So in that sense, there's that connection, but I don't know about broader connections beyond that.
Okay, thanks.
Other questions?
Yeah, I have a question. Well,
If you would. We're waiting
I
for
have a question as I go along. So, so what did you do to measure your, I guess, the temp? So this is riffing off some of the earlier sort of questions. I wonder, as a result of this process, if you can look at the degree you've excited your condensate from its scale invariant state. So you take some initial state and you've expanded it out, ideally in a sort of scale invariant way. And now you want to compare the state you want with the actual state you have. And I wonder, it's sort of a little bit related to the question about the squeezing, but I'm wondering, you're going to excite pairs of atoms out of the condensate. I wonder to what degree, or I'm guessing that there's going to be corrections of that form. And I wonder to what degree you could measure that.
That's a very, very
It just appears as a temperature, but if you could also do pair correlation measurements, that would be, that there might be some very interesting stuff, which is related to the quantum anomaly story as well, that Joseph mentioned.
Yeah, so in terms of experimental measurements, I'm not sure. I agree that you could look at least numerically, the deviation of for a given system, the deviation of your out of equilibrium state compared to the one predicted by scale invariance.
What one could do that, you're saying, but you haven't yet.
But we haven't yet, that's right. And I don't know what one would find. That probably depends exactly on how your system violates scale invariance. But maybe there are more general observations to be made there. Yeah, that's another interesting extension.
So at the moment, are you measuring your? So you're not able to. Are you able in any way to measure some degree to which you haven't perfectly got the state you wanted?
So right now we've only explored systems that identically obey scale invariance. We have explored practical ways in which you wouldn't be able to implement a Deltakick and how that modifies your final state. So for instance, if you have a state of, if you are doing Deltakicks of finite duration, then you see some deviations of your final state compared to the one you wanted to prepare, but not yet because of how our system has violated the assumption of scale invariant dynamics.
I kind of think that Duncan is asking an experimental question and David's answering about the theory. So maybe we should specify that experimentally, all we've done is we've seen, let's smack the thing and see how cold we can get. And we've done that not even with a harmonic oscillator, but with a Gaussian, hoping that the harmonic oscillator approximation was okay. And we just measure the temperature, the expansion rate, nothing else. And we never do repulsive kicks because we don't have control over the detuning. So the theory work is really very separate right now from anything we've measured in the lab. We could certainly ask.
The repulsive stuff is all theory.
That's right. No,
Correct.
we haven't even experimentally implemented Deltakicks with a repulsive potential. All of these Deltakick examples I was showing you at the beginning of the talk were with a single kick that's, well, sometimes two kicks, but they're all attractive potentials.
I see.
So even experimentally,
So the question.
even experimentally in the ideal Deltakick construction, repulsive potentials haven't been incorporated, let alone, trying to compare what an exact scale invariant Deltakick would look like compared to the classical construction.
And first, we'd want to get rid of the aberrations and maybe be sure that our initial state actually looked like the way we model it, and that the potential really was harmonic. And if we did all that, maybe the first thing to look at, if one wanted to study what you're raising, is just the time dependence of the final state, right? Have we actually ended up in a stable state of the new potential? If so, then it'll just sit there in that new potential. And if there's any residual breathing, it seems to me that would be a first sign of a deviation from adiabaticity or perhaps scale invariance. But as for looking for any beyond mean field effects, yeah, I suppose one could imagine starting to look at that correlations and so forth, but talking about much more complicated experiments, we have no current plans in that direction.
I think there's a lot in this. It's really fascinating, but maybe they're somewhat in the future then. But yeah, there's a lot of interesting directions. Yeah.
Yeah, we agree. In particular, our hope of not just improving the speed, but of improving the cooling performance from these aberration canceling in analogy with lenses, we're particularly excited about.
Yeah.
Any other questions?
Yes, please. So going back to my original question, I just wanna understand. So again, completely theory now. You're solving a system that obeys scale invariance. Solving the Yermakov equation gives you essentially the time evolution of a state given some form for omega. So far, okay. Now you're saying during that process you accumulate a phase, and this phase you would like to cancel with a delta kick. Is that correct?
That's right, and that phase is what encodes the excitations of the expanding cloud. Sure.
Then here's my question: how is that related to shortcut to adiabaticity?
Well, so if I can cancel that delta kick, then I am in an equilibrium state with respect to some final harmonic oscillator. And I've done that protocol faster than a standard adiabatic evolution, which would require me to, ramp the harmonic oscillator down very slowly. So that's the sense in which Deltakick cooling is a shortcut to adiabaticity, because it's just a faster protocol.
Sure, but then you can compare. I mean, you can compare everything here with delta kicks to what's called counter-diabatic. And I mean, I'm just asking whether that is sort of gives you. I mean, if whether that would give you better or worse cooling at the end.
Better or worse cooling. So that if both protocols lead to the same final state of the harmonic oscillator, then the cooling performance is identical.
No, but now there's a question of time, right? Because you wanted to make things shorter, essentially.
Right. So so my understanding is that bang protocols have been demonstrated to be the time optimal protocol given some bounds of your the time dependent harmonic oscillator. that you can implement. And so Deltakick cooling is like a bang-bang protocol, assuming that you have access to an infinite trap frequency. Because in order to implement a kick, a Deltakick, a kick that's instantaneous in time, you need an infinitely large or an infinitely strong harmonic oscillator. So in that sense, Deltakick cooling is equivalent to bang-bang protocols where your trap frequencies are unbounded, where your accessible trap frequencies are unbounded. And so it's by this equivalence that Deltakick cooling is time optimal in that it's equivalent to the bang-bang protocol with unbounded trap frequencies. Now that's sort of the intuitive explanation. The proof of bang-bang protocols being time optimal are given in these two papers. The one in 2009 for real trap frequencies, the one including imaginary trap frequencies in 2010. And then in our work, we actually, calculate what these times are for our Deltakick cooling sequence and show that they're equivalent to the bang-bang protocols with unbounded trap frequencies. I hope that was maybe a little bit helpful.
Yeah, thanks.
Yeah.
Are there any other questions? I see Duncan is still typing, but
just sort of thinking aloud, but I suspect the fact that it's not really an infinite harmonic oscillator will have some effect, like introducing some scale invariance into the problem. So sorry, some scale breaking,
right?
Effect.
So you do need the trapping potential to be harmonic for scale invariance to hold. Turns out it also works with a linear trapping potential. But although the scale invariant equations are slightly different, but different trapping potentials, other types of anharmonicity, I don't believe generally obey scale invariance.
Right. And the same will go for the inverted harmonic oscillator. Of course, I mean, eventually you need to regulate that at large distances and through a sorter potential or something that flattens off eventually, and that will also break the invariance. Yeah. Mm-hmm.
And also ruin the Deltakick.
Right.
Both things would occur.
Thank you.
Right. Well, if there are no other pressing questions, let's all thank David again for a talk that obviously stimulated a lot of discussion, and I hope was clear and interesting. And thank you all for your participation and questions. I'm going to have to start looking at these references, as are the rest of us. So have a good rest of the day, everyone. Nice job, David.
Thanks, everybody.